All right, this is probably one of my favorite lessons before you actually get to calculus, because I was excited when I first taught this concept in Algebra 2 or college algebra at the college level. And what we're talking about here is how can we sketch a function knowing just its equation? And in Algebra 2 or college algebra, they looked at various properties, and you got a very good, very reasonable rough sketch of what this picture looked like. And then when you get to calculus, you're going to revisit this topic, and they're going to show some calculus techniques, and they're just going to finish up this question that you've had for maybe a couple of years, depending upon how many, when you took the first time you saw Algebra 2 versus when you're going to see calculus. And so I thought it was a great idea to go back through and remind ourselves of some of the topics that were addressed in graphing higher order polynomials. So the first thing that I want to look at with you is just how to find intercepts. Okay, pretty straightforward concept. Let me start by giving us an equation here that we will manipulate. So we're going to look at f of x equals x cubed plus x squared minus, let's see, 4x minus 4. Okay, and I'm just going to remind you of how to find the intercepts, the x-intercepts, and the y-intercepts of this particular equation. The y-intercepts are very easy. You simply find f as 0. Replace x with 0 everywhere, and whatever number you get, that's where this thing crosses the y-axis. So for our sample problem here, it's going to cross at -4. Which means I know an ordered pair, 0, -4, that this thing crosses the y-axis at. The x-intercept, now this can require a little bit more effort, and there's a couple of more advanced techniques further on in this particular section that I'll remind you about, but this one works out nice. So what we're going to do is we're going to set it equal to 0, and then we're just going to solve for x. And we're going to take advantage of factor by grouping to get this job done. So I notice the first two terms I can take out an x squared, that's x plus 1, and then I notice I can take out a -4, and that's an x plus 1 as well. And then if I group them, I get x squared minus 4, x plus 1. And this, we've done this question before, so that'll give us solutions of -1, -2, and +2, which means it crosses the x-axis at those three numbers. Okay, end behavior is another topic essentially related to leading coefficient. So looking at a general polynomial here, f of x equals ax squared plus bx plus c. And this is just a general quadratic in this case, but the leading coefficient is that front number. Okay, and there's two types of patterns that it could be. The leading term could be something to an even power, or the leading term could be something to an odd power. Okay, and even powers like x squared, x to the 4th, x to the 6th, stuff like that. Or it could be a negative x squared, a negative x to the 4th, or a negative x to the 6th. And in those cases, if it's an even powered and it's positive, then it's going to end behavior is going to be in the first and the second quadrant. Now, what I mean is, in the long run, is you're looking at large x values, the y values tend to be really big in the first quadrant and really big in the second quadrant. Now, in the negative case, where the leading coefficient is negative and even powered, then your end behavior tends to be the third and the fourth quadrant. Okay. Now, odd meaning x or x cubed or x to the 5th or x to the 7th, or just an odd powered exponent, or its negative counterpart, so negative x, negative x cubed, negative x to the fifth. Okay. In the odd case, in the positive odd, it goes in the first and the third. And in the negative odd, it goes in the second and the fourth. And again, these just describe how do the y values tend to behave just as they're heading off screen as far as the picture goes. Okay. All right. Next would be wiggle versus bounce or multiplicity. So let me kind of remind you of some definitions. And you might not have encountered this. This is kind of a term that I have encountered at one of the colleges I teach at, and I just have embraced it because I love the idea that functions wiggle or bounce based on the roots or number of times it crosses the x-axis. So let me give you a made-up function just so I can illustrate the difference here. So we're going to do x plus 1 squared and x minus 2 cubed. So it only crosses the x-axis twice, but there are multiple roots of that same form. So in other words, this particular function would cross the x-axis in -1, but it's got what's called a multiplicity of 2, or an even-powered multiplicity. And x equals 2 would be odd-powered multiplicity, so it would be a multiplicity of 3, meaning this particular function actually has 5 roots, because it's an x squared times an x cubed, which is x to the fifth. But in those 5 roots, 2 of them are -1 and 3 of them are positive 2. Okay. Now, which one is the bounce, which was the wiggle? And then I'll kind of go to a graph and kind of illustrate this. Bounces are even-powered multiplicities. I like to think of it like this. If you take a negative number, or you square it, or you fourth it, or you sixth it, a negative always becomes positive. Okay, so in other words, it doesn't switch y values. It stays, the negative form and the positive form both match. Maybe a graph will be better to show that. But the even-powered, those are the wiggles. Okay, so what on earth am I talking about here? Let's just take a look at this graph, and let me highlight out the roots in it. So we said at -1 it crosses, and at positive 2 it crosses. Okay, little side conversation, since we already kind of talked about intercepts and multiplicities. This thing has got an end behavior. So it's got an end behavior. It's going to look like a 5th degree polynomial. So 5th degree means up in the first quadrant and down in the third. Okay. The other thing to notice is if I find f of 0, so f of 0, which tells me the y-intercept, would be 1 squared times -2 cubed, which gives me -8. Okay, so I actually can put a third point in the picture down here at -8, because I know it crosses there. Okay, now what does that have to do with anything? Well, I know, since I know where it crossed the x-axis in the first quadrant, I know at this point it's going to be going up in the first, after it leaves the x-axis, and I know on that first root at -1 it's going to go down into the third quadrant. Okay, and I know because it's got a multiplicity of 2, then it's going to bounce off the x-axis, and that's what bounce looks like. Kind of write that down here. So bounce literally says it hits the x-axis and reflects it, goes away from it. And I know because it's an odd multiplicity at 2, then it's going to wiggle or cross through the x-axis at that other root of positive 2. Okay, and then from here I can sort of, like a puzzle piece, I can connect the pieces and get a very quick sense as to what this graph's doing. So I know it's going to connect here, and then it's going to come through. I know it's got to turn around somewhere at that -8, go through here and end up going that way. So that's a pretty rough sketch. Okay. Now, what is calculus going to teach us? Calculus, this is a rough sketch in that there's actually more detail in the actual graph that we just don't know about. And let me just kind of point this out here. This piece right here was an estimate. I know it crossed at -8 because that's the y-intercept. I don't know if it turned around there. I know somewhere it's got to, when it's leaving that first root and it's going to go into the second root, it's got to change directions. I'm not quite sure where that is. That's what calculus is going to teach you. When you get to this unit, you're going to think back to this lesson and go, oh, that's what Soleil was talking about there. So somewhere there's this turnaround point. We don't know what that is, and that for us right now, it's just an estimate. But later on in calculus, they'll kind of get you there. Okay. Let me keep going with a quick review of synthetic division. Okay. So let's say, let me kind of set up a scenario here, and then I'm trying to remind us of synthetic division, and then in the next slide, or the next page, I'm going to go through the rational roots theorem, and that's kind of why we need synthetic division. But let's say, for whatever reason, I give you this polynomial of x cubed plus x squared minus 4x minus 4, and I would like to know, if I divide x plus 1 into it, what do I get out? Okay. Synthetic division was this nice little shortcut, and instead of doing polynomial long division, allows us to quickly divide in and figure out if it's an even factor or not, and then what's left over if I divide out that common factor. So with synthetic division, I'm going to collect up a list of my coefficients. So x cubed, x squared, x, and a constant. Every position has to have a number. So if I don't have something in the initial polynomial, then I'm going to leave 0 there. In this case, I actually have something. So the coefficient of x cubed is 1. The coefficient of x squared is 1. The coefficient of x is -4. And the constant is -4. Okay. And then I'm going to synthetically divide in a number, and that number is defined by this denominator. So where it says x plus 1, if I take x plus 1 and set it equal to 0, and actually solve, I get -1. So I'm going to synthetically divide in -1, which is going to translate as the same as dividing in this x plus 1 term. Okay, so with synthetic, we're going to drop the first number, and then I'm going to multiply across. So -1 times 1 is -1. Then I'm going to add, or combine like terms, depending upon how you want to think about it. In this case, gives me 0. Then I'm going to multiply, so I get 0 there. Combine like terms, get -4. Multiply that again, you get 4. And then combine like terms, and I get 0. Okay. Now, this actually told me something. The fact that my last position was 0 says that this evenly divides in, and this piece right here is my result. Okay. So if I write this out here, so if I take x cubed plus x squared, plus x squared minus 4x minus 4, okay, that factors into x plus 1, and then this other piece, okay, notice if I take x cubed divided by x, I should get x squared. So this first number is my x squared term, so that's x squared. Then I have 0 x's, and I have a constant of 4, so x squared minus 4 is what it factors into. Okay, and that's pretty much all synthetic division is good for right now, is quickly telling us whether something is evenly factorable or not. Okay, and that brings us to rational roots theorem. Okay, so up to this point, it's been very nice and very helpful if we can factor something easily, identify where it crosses the x and y axis, look at end behavior, look at multiplicity. Those are some nice, great things that if it's built into the equation, great. But what happens if it's not so easily built in? Let me give you an example here of something that's going to require a little bit more effort on our part. And I've been writing in blue, so let me stick with blue. Sorry, that blue. Okay, so if I give you f of x equals x to the fourth plus 2x cubed minus 5x squared minus 4x plus 6. Okay, so if I give you something a little bit more complicated like this, and I say factor it, we got a problem. Factor by grouping doesn't work. A lot of our, nothing works, right? We don't have any brilliant idea. But if this thing is factorable, so if there's some way to take out a binomial of some kind, and it so happens that these numbers are rational roots, meaning they're not decimals, they're not, they're nice, pretty, they're fractions, they're something that we can handle. Where would I go to get my numbers? Well, I would go for this position and this position, what should be related to, these four positions as far as factoring goes. Okay. Now we're going to call these, for reasons that might make sense if you've if you remember looking at this in college algebra or in algebra 2. We're going to call this position Q and this position P. And I'm going to make a list of all the P factors. So factors of 6. So what multiplies to give me 6? Well, either 1 and 6 or 2 and 3. And then I'm going to look at this for Q and go factors of 1. Okay. So some textbooks you might hear this called the PQ process instead of rational roots theorem. The technical name is rational roots theorem, but we're going to do the PQ thing. Has a little flair to it, I guess. And what I'm going to do is I'm going to write down a plus or minus list of all the numbers of P over all the numbers of Q. So in this particular example, it's not that bad because we have just one number for Q. But if it was, say it was 1 and 2, or if there were more than one number, we would literally take everything of P divided by everything of Q and just make a list of this. So our possible factors would be plus or minus 1 over 1, plus or minus 6 over 1, plus or minus 2 over 1, and plus or minus 3 over 1. Okay, those are all the different possibilities that we could try. Okay, that's a fairly decent list. We have, 8 numbers to pick from. It goes back to, why do I need synthetic division? Synthetic division will quickly let me see if something is a factor or not, so I can factor it. Okay, so I'm going to make a list of my coefficients for synthetic. So x to the fourth, x cubed, x squared, x, and constant. And I'm going to, this is an honest to goodness statement, I'm going to randomly guess one of my 8 numbers, either positive 1 or negative 1, or positive 2 or negative 2, or positive 6 or negative 6. And it is a flat out guess. Right now I don't have any significant evidence. Now you might, in your class, you might have talked about Descartes' rule of sign, and that'll help narrow down some of the choices. But that's another mathematical analysis that I'm just not going to go into for this lesson, considering that this particular topic doesn't come up a lot. It comes up enough that it's a good tool to have in your toolbox. But if you want to look up more detailed and all sorts of fun things, you just go Google rational roots theorem, Descartes' rule of sign, and you can get more information on how that works. Okay, so let me collect up all my coefficients here so I can actually do this. So I've got a 1, a 2, a negative 5, a negative 4, and a 6. And like I said, I am going to guess. And I don't want to waste your time here, so I'm going to guess intelligently, meaning I kind of might know the answer ahead of time. I'm going to guess a 1, and I'm going to do synthetic division on it. So drop the 1, multiply, combine like term, multiply, combine like term, multiply, combine like term, multiply, and then we end up with 0. Okay, so that then says that whatever I plugged in, whatever I used, was actually a root. And so I used 1. remind you of this, I used if x is 1, which means the factored form of this is x minus 1. And I'm left with, so the 1, 3, negative 2, and negative 6 would be x cubed, because it's one less degree than the original, so not x to the fourth, but x cubed, plus 3x squared minus 2x minus 6. Okay, so that's all rational roots does, is it gives me some options to figure out for a common factor, allows me to test it, and then if it is factorable, it gives me a smaller thing. Okay, and so from here, this particular cubic, maybe we want to try factor by grouping, or maybe we go right back into P's and Q's and we just do some good old-fashioned guessing and checking and see what's going to happen here. Alright, so we're going to do just a couple of practice problems and see if we get the big idea, if we remember this from previous classes or not.